as we saw, proteins or polypeptides are amino acids that are joined together by peptide bonds. When we write them down, we always list the amino acid that has a free amino group first, and then we list them in order until we come to the last amino acid, which will have the carboxylic acid group free. And we call the first and the last the N-terminal and the C-terminal amino acids. The order of the amino acids in the protein is called the primary structure. But because the polypeptide's extremely large and has a very complicated three-dimensional structure, we use 4 different ways to describe it. So the primary structure of a polypeptide is the amino acid sequence. Then there is secondary structure. Secondary structure is hydrogen bonding between peptide bonds that causes a regular repeating structure. We have an alpha helix or beta pleated sheet that are caused by hydrogen bonding between peptide bonds, and these are both secondary structure. Then we have tertiary structure. Tertiary structure is interaction between the side chains on the amino acids, and it causes the protein to fold over into a particular shape that is, we call it a globular shape. It's like a big ball, lumpy ball. And there's quaternary structure, which is the interaction between multiple chains. For instance, in hemoglobin, we have 4 different protein chains. Those 4 different protein chains are held together in one hemoglobin by interactions between them, and we call that quaternary structure, where it's chain to chain being held together. Here is an image of secondary structure. Here you see a peptide bond, and here you see a peptide bond. This is an example of beta-pleated sheet hydrogen bonding. It's between peptide bonds. When you have this in proteins, you might have 3 or 4 chains aligned together like this, making a little flat area. You can have big, long chains of this in some structural polymers. For instance, silk is all beta-pleated sheet, and it makes a very strong thread because of it. Tertiary structure is the folding of the protein into a lump. So the polypeptide folds over because the side chains, the residue groups, interact with each other and are attracted to each other. There's several different types. First of all, you can have a disulfide bonds. This is a covalent bond between 2 cysteine molecules, and it's very strong, and it'll tie 2 parts of the protein chain together at that point. You can have hydrogen bonding between side groups and between side groups and peptide bonds. And this might be, let's say, where an amine functional group on a lysine might hydrogen bond to another amine on a lysine functional group or something like that, or maybe to a serine alcohol group. Then there are ionic interactions, and this one's relatively strong. Amine groups on side groups and carboxylic acid groups on side groups are ionic because the amine is going to be in the ammonium state, so it'll have a positive charge, and the carboxylic acid will be in the carboxylate stage with the proton off, so it has a negative charge. And those can tightly bond in an ionic bond to each other. It's tight relative to a hydrogen bond, at least. And so that actually makes a pretty good, strong attractive force between 2 parts of the chain. That sometimes is called a salt bridge because it's like a salt, a positive and a negative. Then the weakest of all interactions is hydrophobic to hydrophobic conjugation. What this is where there's a carbon chain, so all carbon hydrogen, nonpolar, and a carbon chain, all carbon-hydrogen nonpolar, are close to each other, and so they tend to snug up with van der Waals forces. Okay, so here are two cysteines, and let's see how they can form a disulfide linkage. A thiol and a thiol, they're oxidized, so they lose two hydrogens and form this disulfide linkage. Now, proteins form enzymes. In fact, most enzymes are proteins. The enzymes speed up spontaneous reactions, or they catalyze a reaction that needs energy transfer because it's non-spontaneous. When it requires energy transfer, you use ATP going to ADP, and that provides the energy to put into this uphill reaction. Enzymes catalyze because they have active sites where the substrate fits in, maybe with another substrate, or it's maybe modified by the enzyme in that active site. There's different types of things that can go on. And through the substrate fitting in that active site, the reaction occurs. If the substrate can't fit in that active site, the reaction won't occur. If something else gets in the way by either fitting in there as a competitor or by modifying the protein shape, then the substrate can't undergo the reaction and catalysis won't occur. So this gets us to the point of denaturation. Denaturation is the loss of the tertiary structure. The tertiary structure depends on hydrogen bonds, ionic bonds, hydrophobic attraction, and also the disulfide linkages. Denaturation is when you change the shape of that protein. That change usually changes the shape of the active site so that substrates can't fit in there any longer, and then the protein's no good anymore. Disulfide linkages are really strong in their covalent bond, but that's only part of the tertiary structure, so you might only have to lose a few hydrogen bonds, maybe only one, and you might have denaturation. And disulfide linkages are susceptible to heavy metals inserting between the two sulfurs, and that lengthens that connection, and it can cause loss of tertiary structure. That's why lead and mercury can be deadly, because they will modify the enzymes in your body. So tertiary structure is easily disturbed by changes in pH, because that will change ionic linkages, that will change hydrogen bonding, that will disrupt any alpha or beta, alpha helixes or beta pleated sheets that are part of the protein structure. Changes in temperature will cause tertiary structure to be messed up. If you get it too hot, the protein molecule will wiggle so much that hydrogen bonds and other linkages can be broken. If you get it cold, it might crystallize and break certain linkages. Solvents, such as nonpolar solvents, or some solvents like that could get in there and hydrogen bond to various places, will destroy tertiary structure by messing these linkages up. And last of all, most importantly, is reactions, especially redox, can change functional groups, which would then change tertiary structure. A tiny change can have a drastic effect on the enzyme activity, so small changes can cause denaturation. And once you have that change, it usually is impossible to bring that tertiary structure back.